So my name is Rapahel Cohen and I'm from Chorus. I'm going to speak about speaker identification. By the way, we're also a Python shop as well, but without the Redis thing, which sounds cool. So I'll jump to the problem that I'm going to describe, and then I'm going to work backwards from that. So what is speaker identification? If you go to academia, you would find these two disparate communities that what they're trying to solve is this. We have this list, we get an input of a recording, and we want the output to be a list of ranges where we say who spoke when. So this sounds pretty simple. We have Alice and Bob speaking to one another, and we want to be able to say that the blue dots are Bob and the yellow ones are Alice. Why do we want to do that? Because in this case we're eavesdropping in the middle, and we want to be able to know who said what. So this is two different communities when you go to speech. One of them is called diarization, where people try to identify all of the ranges. So we want to say this is speaker 1 and this is changing to speaker 2. And the other community that does that is called verification, where they care, given one of these segments, to say who is the speaker, or to say I'm pretty sure this is Alice. So I'm going to work backward now, and the big question is why should we do that? So at Chorus.ai, we help our customers record their conversations with their customers. Speaker separation is pretty important for that task. First of all, when we do that, we are going to turn the data into text, and separating the people helps those algorithms perform better. Afterwards, if you look at the example here, when you get a call and you want to browse around and see what happened in the call, having the separation can really help you find interesting spots or see if anything was said by the person who works for you or by the person who is your customer. Finally, down the line, we want to identify things such as long monologues. In this call, we can see that Joe spoke for a really long time. He didn't pause to listen to the customer, and you should probably work on that, to listen to the people that you're talking to. Also, this is very useful for predicting whether the customer is going to buy from you, or are they happy with your representative. And this comes in engagement. So when we see these bits where everybody are talking and they're talking to one another, this is a very good sign. It means that people are asking questions, they are interested in the conversation, they are not just waiting for it to be over so they can go to their next meeting. So a little bit detour into the motivation. So understanding conversational speech is useful for many applications. We all know AI agents such as Alexa, Google Home, Siri. If you work in nuance, you might be transcribing physician notes for practices in the US. Or our business is to guide humans in having better conversations with the people that their company works for. Our medium is sales conversation. This is usually on conference lines or phones, so people phone into a WebEx or a Zoom and have a conversation with their customers. Most sales cycles, according to Salesforce, it's about 92% of sales include some kind of phone call or conference call. This is natural speech. It has no restrictions, so this is not Siri. It's not easy like Siri remind me that X, Y, Z. So we don't know what they're going to say, and we can train them like Siri or Google trains us to learn what sentences work. And we are looking at sales calls which sell things which cost thousands of dollars or more, so people care about these conversations. These aren't just the hot representatives calling you to bother you to switch from yes. These people worked hard with their marketing to get the customer into the conversation, and they care about the output of that conversation because it costs them a lot of money. These are usually 10 to 60 minutes long. And right now in Chorus we have thousands of users, and we record an hour of audio every 10 seconds. So the algorithms, have to be scalable. And we've already recorded over 2 million of these. So now we have the data to do some interesting stuff. So what are the kind of questions that our framework can help you with? You can find and share important moments. For example, the customer asking about security. So if you're JP Morgan and you are talking to a customer and you want to see where do security concerns come up, you can use the topics that we identify in the text to see where the prospect talked about security. If you want to coach your representative effectively, you can help them find the best 10 answers that people answered about what's double authentication. We can deliver the call summary and key points automatically. For examples, if you mention that you're on your to-do list is to send the customer some kind of material, you'd get an email reminder about that. We can provide live guidance. So if the customer mentions security, we can pop up this message that says, remind them that we are GDPR compliant. Is everyone here GDPR compliant? JP Morgan? Hope you are. We have 20 days more, right? Provide marketing and product with a direct view of what the customer's needs and wants and wishes. So right now, this is one of the biggest value points that didn't exist before this kind of tools were around. When you are trying to decide what the company should build, in the old way the tech works, or any industry, you can bring in some few people and ask them what do they want. You can send out people with questionnaires and ask them what do they want. But actually all of the sales conversation that your salespeople are having used to be thrown away. Nobody could go over all of these and see what happens. So if I want to see how many of my customers care about GDPR, if you don't have this kind of technology, you just can't. You can listen to 5 calls or 10 calls or 100 calls and say, this was mentioned 3 times or 4 times. Using our software, you can go to all of the sales calls and just write GDPR, and you'd see all of the cases that it mentioned. You can see whether the sales calls where this is mentioned, you are getting more wins or not, depending on the answer. So this can really help you shape your product for the future, given the real customer feedback. Okay, so we're done with the motivations. We want to answer all of these really cool questions, but I don't know if you've seen the thread. They're all based on someone saying something. So the what part is solved by our great automatic speech recognition. We have our own speech recognition built in-house. It's pretty cool. It's better than what you get if you just go to one of those APIs, and it's trained in domain. And the who part is what we're going to do today. So speaker identification. Why can't we have nice things? Why can't we know who's speaking from the systems? So first of all, usually we use Eve, which is a recording agent. Our software joins your calls and records it. Some of the calls come to us from other recording agents, and they tend to record mono channels as well. Why? This is, again, historically the way that phone systems work. They really like mono, and it kind of moved into the world of phones over IP as well. Another reason that we want this, we may have multiple people speaking in the same room. So they sit next to the speaker, and there might be 2 or 3 of them, and it might even be that one of the representatives is physically at the customer's place, and some of the others are remote. So we don't know who the people are in each room, and we want to identify everybody and also easily browse between the speakers. Finally, when we get there, we're going to do same room recording in order to provide all of this wonderful technology for field salespeople and not just remote ones. So let's get into the technology. What's speech? I'm talking right now, and this is a type of speech. It's a time-varying signal with multiple layers of information. So this sounds really cool. I'm saying some words. I'm providing emotion. Hopefully, I'm not all flat. You can listen to my voice and find some properties about me, maybe my height, my weight, my gender. Also, you can find some discourse and entrainment cues. This means if I stop talking and I say, does anybody know what entrainment is? You see, so some of you marked that you don't know. It means that I'm giving you cue for what I'm expecting you to do. I gave you a cue that I'm expecting an answer. So all of them come together inside the speech, and this information is conveyed in some sort of frequency over time that my vocal cords are producing. So what's an end-to-end speaker separation? We're going to present our method for identifying the speakers and where it differs from what you'd see if you'd search online for diarization or verification is that I care about getting that first picture that we had in the beginning where you can see where everybody spoke. I don't care just about the speaker separation or just about the deep learning part that we have somewhere around here or just about the clustering. I want to put this all together into one working system. So we're starting with voice activity detection. Luckily enough, this is pretty much a solved problem. We want to identify when people are speaking. We start with separating silence from noise, which could be any kind of speech or trains going in the background or your dog barking while you're connecting to your WebEx room. And after we did that, we want to identify the difference between speech and non-speech incidents. For this, we use the GMM approach, the classical way to do that. I think it's been working, I see here 2013. So this is nothing very recent. And we fit two GMMs, one of them to the noise example, another to the speech example. And then we just do a Bayesian likelihood and decide for each frame whether this is speech or noise. If you want to build this at your house, it's good to train on your own noises. Mark a bunch of places where your recordings have noises. It could be different noises. In our case, some people like to have meetings in cafes, so background chatter is something that you want to eliminate. So you add this to the training data. You can do this in Kaldi, which is the open source speech processing environment that we use. Pretty simple. Next thing, we want to extract some features. So I'm not going to dive too much into that. MFCCs are the standard classic way of turning speech into features. They correlate to the way that we separate sound in our ears. So these are, again, 60s, 70s technology, I think. There are a bunch of ranges of audio, and each of them is sampled for the decibel over these short periods of 40 milliseconds. So now we're going to get into the interesting parts. So we have these small frames, windows of voiced frames. Each of them is 40 milliseconds long. And we have the MFCCs, which are just a vector of numbers for each of the frequencies, what were the decibels. And what we're going to do is a bottom-up approach up to a certain point where we're going to try and identify inside the call which overlapping windows are the same person speaking. So this is going to give us these small ranges, 1 second ranges or 2 second ranges, where we're pretty sure it's the same speaker. The approach is, again, a Gaussian approach because this is not an extremely hard problem. When somebody speaks for a second, it's pretty consecutive and it sounds very similar, and we can fit a Gaussian to the window. It doesn't have to be a GMM like before. It's just a simple Gaussian, and using the information in it, we can decide for each of these tiny frames of 40 milliseconds, are they the same speaker or not, based on the KL divergence between them. So again, this is pretty simple mathematically. If you go to the reviews from 8 years ago, this is the prime technology used back then. So we use it to create these 1 second segments where we are pretty certain that this is the same person speaking. The next step, this is the step I'm going to delve into, is called the I-vector embedding. We want to identify that a certain second belongs to a speaker, and we want to do it by representing it in a lower dimension. Now, this is in Hebrew, but This is a piece from Franzen's book called Corrections. It came out in 1999. And one of the characters, which things end very badly for him in the book, has made $20 million from building this program called Eigenmelody by embedding music into a low vector space and then allowing people to search it. So basically, Franzen is describing Shazam in 1999 with the right math and everything. So the math has been around, and this guy knows how to do research. Seriously, it's good stuff. And what I'm going to describe now is how to extract these vectors, which I'm not sure he was completely right about in 1999. So where do I-vectors begin? We go back to 2011. The original approach is based on still GMMs. Deep learning is only picking up at this point, and GMMs rule the earth, or at least the speech industry. And what we want to do is take these 1 second length windows that we are pretty sure are the same person, and we want to represent them in a small space. So we have all of these tiny 40 millisecond frames, and we want to combine them into one vector so we can easily say that this is the same speaker and compare them to one another. So the idea here is to train something called a universal background model. A model that says how do people sound like, where each of the speakers is drawn from this model with just their parameters. So each person is just a parameter version of the universal model of speech. And at the end, it's going to compare people using some kind of Bayesian score or learn some kind of cosine distance using SVM. So this is really, by the way, if you open the paper, it's super complicated. They're using things like front-end features and UBM and I-vector extractors, and none of it is very well explained in the document. Now, this is lucky for us because you can replace all of that stuff with deep learning. So we have training data. We have these audio segments that we have the speaker marked. So we say this is speaker 1, this is speaker 2, this is speaker 3. And we're going to learn the framework of the network is simply an embedding layer followed by a DNN, followed by a softmax layer that points to all of these speakers. So we have in the training data 1,000 or 2,000 speakers, and we want to simply train the network to say that each of these segments is the right speaker. We're going to train this by predicting known speakers, and we're going to propagate the loss from this point back to the embedding function by seeing when it gets it right and when it gets it wrong. Finally, we're going to drop the DNN and the softmax and everything that we learned, and now we've got this really great embedding function that can work in the wild. It doesn't have to be those same 2,000 people, because we assume that it learned, if we make the embedding small enough, it's going to learn about what people sound like. Now, does anybody know what the problem here with the softmax layer and predicting everyone could be? So it's going to do some overfitting, but mostly we are predicting a huge space of 2,000 people, and the softmax layer gets really large. So it's not very a good way to learn things.
Yeah, it can be more than 2,000 people, no?
No, yeah, because it won't scale for the learning. You can predict 2,000. When you predict 2,000 labels, you're already taxing the learning system. You have to go to hierarchical softmax and start doing all these weird things that people do in word embeddings, but it doesn't scale very well. It doesn't learn very well if you make it big, so you can't. Even if you have 100,000 speakers like Baidu in the paper I'm going to show in a second, it just won't work with that kind of network. So what are we going to do? Instead of predicting 2,000 speakers, we're going to predict one label. For each learning instance, we're going to take 2 audio segments, and they're either going to be from the same speaker or from two different speakers. Now we're going to embed each of them using the same network, and then predict whether this is the same speaker or not. So we turn the problem from a problem where we are using a softmax layer to predict some 2,000 labels. Instead, we are going to predict every time 0 or 1. Is it the same person or not the same person? So these are Siamese network. The approach was invented by Jan LeCun. At the same year of the I vectors, people try to do that in speech, but without the whole I vector theory behind it. And in 2017, a very similar model was shown in academia by Snyder and Povey. So we have the Siamese network, but what's the problem here? Most people don't sound exactly the same. And also we are learning a classification problem when what we want to learn at the end of the day is a similarity problem. We want to know when examples or samples are similar and have a distance function. So instead of learning a classification problem, Lee et al. From Baidu are suggesting to use triplets. We have the anchor, which is the real person. We have two samples. One of them is that person, and one of them is a confounder. And what we force the model to learn is the right cosine distance. So the cosine distance learned, it punishes it when the anchor is too far from the positive example and too close to the negative example. The good thing here, we are going to learn a cosine similarity, so we don't need anything afterwards. We've already learned something which is a similarity. The embedding function now very easily can be used to compare new samples which are, out of domain, out of sample, whatever. This allows Baidu to learn how to compare, I think, about, it's not written here, but they are using some 120,000 people, I'm sure only for good purposes. Same thing from Google. So this came from a diarization community, but in the verification community in Google, they're doing the same thing, but they're adding this little tiny thing. Instead of just picking two samples, one of them that person and the other one is random, each time we take the speaker which sounds the most like that person. So it would have to learn to distinguish very similar voices and not just have an easy task and not learn enough. So instead of randomly picking the confusion samples, it samples it from the most similar speaker. And this is very similar to FaceNet in vision. And the approach itself is very similar to other triplet similarity approaches that you see in the literature. Okay, so we know about I-vector embedding and how to do it with deep learning, but how do we assemble our system from that? So the next step is clustering. We have these short segments. We've embedded them into a really cool vector that separates them well in space. And now we want to create a cluster per speaker on the call. You can do this with agglomerative clustering. You can do this with k-means. It works pretty much the same. And one of the problems here is once you have a few segments clustered, how do we score the distances? When do we stop? We don't actually know how many people there are on the call. Some of this is just data managing, switch to a smarter distance metric such as PLDA, or you can learn the cutoffs in your in-domain data. So when should you still combine two neighbors in neighbor joining in the agglomerative clustering, and when should you stop? So we have the clusters, and now we basically solve the diarization problems. We have a bunch of speakers. Now we want to label them with names. So how do we do that? Given an audio sample, we want to match it to known speakers. We automatically learn the voices of recurrent users. I mean, the users are paying us. They are making multiple calls. They are on most of these calls which they place. So it's very easily to find the right person within all of those calls and automatically identify their voice in a later call using the cosine distance which we learned with the verification problem. We can also augment the speaker with name. If this is a video conference, you type in your name or your email, we can see who you are. You can further, if some people are not known, you can use text classification on the automatic speech recognition, the text that we got from the voice. in order to decide whether this is the representative or the prospect. So we combine all of these things together in this big soup until we get this result. So here we have 5 people, 2 of them are sitting in the same room, 2 others are calling in on different machines, and we can still separate them all and guess their names. Worst case, we say this is a speaker, or if we use the text classification, we can say this is one of the representatives, but we are not sure what her name is. So the result, we can see who spoke when, how long for, and how much of the total time of the call did they dominate. This provides useful information for the customer in order to do training, search, see what the customer said and not the rep, and everything that I mentioned before. Thank you. Just on time, right? Just to mention before we go to questions, we have another meetup on the 8th where we are hosting the CTO of trucks. It's going to be really cool. We'd love to see you there. Person in the last row.
Yes. So I'm curious how you handle the fact that you don't know at the beginning of the call how many speakers there are.
So as I said, we learned the result of when should we combine a cluster with another cluster. You cluster it and you get these small clusters that you are 100% sure of, the similarity is skyrocketing, and then you have at some point to decide, am I going to mix these 2 or not? And this is, you just learn it empirically from the data. Yes?
What do you do when more than one person speaks at the same time?
We're going to assign it to one side or the other. Yes?
Do you also learn the tone of the speaker? He's angry.
Yeah, I actually spoke about identifying wow moments here about a year ago. So this is actually entrainment, which I mentioned before, finding out what other cues there are in the conversation. You can see it from the frequency changes. When you go up and down a lot in the frequency, this means that you are very engaged or angry. Depends on your culture and your the way that you speak. But in general, engaged is better than bored. Yes?
During this process, they found any challenges with accents and to translate it to the words?
For word, for the text analysis? Yeah, of course, it works better for the majority of what you have in your training data. But what we do is we keep transcribing more calls and adding them to the training data and retraining. So hopefully, we do pretty well on most common accents in the US. But yeah, we have these great customers in Texas, and I love listening to their calls, but the quality probably goes down a smidgen. Yes?
So one thing you'll have, right, since you're doing some analysis on the text, is you'll be wanting to wonder whether or not people are repeating the same thing. Like, how do you differentiate, right? Everyone's been on a call where someone's got the speaker going, and all of a sudden you've got it bouncing back and forth between the two. Can you identify that that's the same speaker? Can you identify that that's what's occurring, right?
Yeah. I mean, if we go back to the example here, we can see same speaker, then it's Mark speaking, then it moves to Kelsey, then Joe again, then Preston, then Joe again, then Grace. Grace speaks for a little bit, then Joe goes.
Sorry, but I'm talking about the specific case where someone's voice is getting bounced back and forth, right? Because
you speak because of the microphones.
Yeah, because of the microphones where it's getting bounced back and forth, right? And in some cases.
Yeah, it can cause errors. Depends. It really depends. When your sound quality is good, you're going to get like ASR. The text is going to be without any mistakes, and this is going to be spot on. If you have really a lot of noise going on, it means that the whole thing might not work. Yeah, that happens. But it's pretty rare. It depends how bad it is and how similar are the voices. If you have 2 people with very similar voices who also have a crazy echo going on, yeah, we may fail. But it works in 90-something% of the cases. Last question?
Yes, to identify is better than a human? Sorry.
Sometimes, yeah, it depends. Depends how closely the human is listening. When you try to annotate this, it's pretty hard in the beginning, but if you listen to the whole call, it's pretty easy. So it depends how much effort you put into that. That's it.
So let's take a 5
Thank you.
break.
Yeah, you can catch me outside.